This morning on large N, following black holes. Sorry.
Um, okay, so let me start off by thanking the organizers for giving me this opportunity to talk about this work that came out like about a month ago with Kazia Budzik and Pedro Vieira. Okay, and these are some other references that I'll talk more about as they come up. So one thing I'll note is this paper came out the same day as ours, and we coordinated because there's some overlap. Um, but they mostly focus on different things. Anyway. So let me first start off by reviewing some basics of ADS-CFT. So probably the wrong color. Right, so we have the usual dictionary of ADS and CFT. Now, in the boundary, if you insert an order 1, also, I'm talking at large N for now. Right, so in the boundary, if you insert an order 1 gauge invariant operator, local operator, it will source a string in the bulk, right? So these would be non-interacting strings because we're at large N. The coupling will be suppressed by 1 over N squared. And in this regime, there's been spectacular success in matching the anomalous dimensions using integrability methods. So this is more or less under control. But now if you start increasing the size of the operators in the boundary, so let's say you go to order N, and then in the bulk, you start putting in heavier objects like brains, right? And one example of this could be that determinant operators in the CFT become giant graviton brains. But then if you go even higher, so go to order N squared, so at this order, integrability will be more or less completely broken. It will be completely broken. And also note that G Newton is scales like 1 over N squared. So when you put in a super heavy object like this, the back reaction is so strong that you can compete with the leading gravitational saddle. So you go from empty ADS to some new geometry. So this is the case we'd be interested in. So specifically, there are some, most of these order N squared operators will source black holes in the bulk. And we're interested in supersymmetric black holes. In ADS 5 cross S5, people have found solutions of black holes which preserve 1/16th of the supersymmetry. So 1/16th SUSY preserving. And they'll be, of course, dual to 1/16 BPS black holes, BPS operators in N equals 4. By the standard ADS 5 cross S5 type 2B and N equals 4 duality. Right, so that's the basic idea. We want to look for operators which could correspond to these SUSY black holes in N equals 4. Okay, so a little bit more about these 1/16 BPS operators. We can classify them into two broad categories. The first one you can think of as is what is usually called in this literature multi-graviton operators. So these are dual to gases of gravitons in the bulk. Right, so of course, like the gravitons are just half BPS operators, and you take products of them, and they'll correspond to gases of graviton in the bulk. And these will also be protected. Some of them will be protected. And people have counted the number of these multi-graviton operators. So the entropy of multi-graviton at order N squared, that is scaling like N squared in energy. These turn out to be something like n to the 5/3, right? And of course, this is less than entropy of a black hole. It scales like n squared. Now, at large n, in fact, these are an exponentially small number of them compared to the black hole entropy. So there must be many, many new operators that are not of the multigraviton type. And the rest, that is the non-multigraviton. And I'm going to call them black holes, all of them. Note that here you could have other possibly exotic objects in string theory, but let me not distinguish between them and call them all black holes. Right. So another thing I should probably mention here is that today I'll only talk about n equals 2 gauge theory. So an n equals 2 non-multigraviton operator. But then the lessons we learn from studying this case are more or less general, and we expect them to hold for other values of n.
Sorry, what is this n?
Oh, this is SUN.
Okay.
Yeah, so of course, n equals 2 is very far from n equals infinity, where we have classical black holes. But in fact, this turns out to be the first example where we can actually find a non-multigraviton operator. OK, if there are no questions about the outline, let me move on. Yeah. You have a question? OK, so let me just briefly review n equals 4. Because not everybody in the audience would be familiar with this. So the field content would be something like you have 6 scalars, and you have 16 fermions, some of them chiral, some of them antichiral. And then you have the field strength, the self-dual field strength, and the anti-self-dual field strength. Right, so all of these are in the adjoint of SUN. And okay, also the indices I, j go from 1 to 4. Alpha and alpha dot are plus or minus. These are the Lorentz indices, SU2 cross SU2. OK, so now local gauge invariant operators are, of course, made out of traces of these. So there would be traces of some polynomials, for example, something like this, and so on. And then you can take many, many products of these. Right. So I'm going to call these the letters, and these you can think of as words. And then you can make sentences out of words. OK. About the symmetries, so you have the usual conformal group, and then in addition to that, you have the supersymmetry. So there are 16 supercharges Q, also 16 supercharges S, which are conjugate. And then you have the R symmetry and the conformal group. But I'm not going to, well, maybe I should also talk about the R symmetry. Where again, Ij run from 1 to 4. These Rijs mix the different Qs. And this is an SU4 R symmetry. OK, so we want to look for 116 BPS operators. So that is states that preserve one of the supersymmetries. So that is something that's scaled by 1 Q. Let me pick a standard Q. Let's say it could be anything. I'm going to call them Q4 minus. And then also pick a standard S, which is the conjugate one. So that will be S4 minus. And yeah, let me also write down the algebra of these two generators, which is OK. Now, as I was saying, we want states that preserve the Q and the S. So that is, this anti-commutator acting on our state should be 0, which means, let me also given name to this. We want things that are killed by delta. And it turns out that such objects should be in short representations of n equals 4, and they have protected anomalous dimensions. Okay, so one obvious fact here is that q squares to 0, because it's fermionic. So this allows us to construct cohomologies under Q. That is, we can look at states that are closed but not exact under the action of Q. Yeah, so construct cohomologies. And this is, in fact, the approach taken by all of these papers here. So let me go into some more details about what exactly is going on there. The idea is to notice that you can identify Q with the exterior derivative D acting on forms, and then the S with the star, and this delta with the Laplacian. Right? So in Hodge theory, you have these objects, and they behave exactly in that way. And therefore, we can borrow a theorem from Hodge theory, the Hodge theorem, which tells us that every de Rham cohomology has exactly one harmonic form. Now, if we translate this to our languages, into our language, a de Rham cohomology is simply a Q cohomology. And a harmonic form is something killed by delta, would be a BPS state. So you can try to find all BPS states by enumerating all the Q cohomology classes. And by this theorem, we know that, yeah, exactly what it says. There are many cohomology classes as well. Yeah, I should probably. Yes. Okay. So this was the program started by Shi Yin and Chiming Chang back in like 10 years ago. And yeah, so they did this explicitly by counting the cohomology classes for SU2, SU3 for up to some charges. So it's computationally expensive to actually construct these cohomology classes because you need to enumerate all the states and mod out by the exact states. Another development in the same paper is that they write down representatives for multi-graviton cohomology classes, which schematically are like this. This is, of course, very schematic. Product over K, let's say. So each of these square brackets corresponds to a graviton, right? So this is a half VPS state. And you take a graviton and you move around in its multiplet. So that is, you dress the graviton with various generators, and then you take products of those. Now, at large n, these are clearly protected because at large n, different traces do not mix. So these correspond to like different strings. So they just mind their business and they don't mix with things. Now, but the point is, as you go from large n to finite n, these still correspond to different graviton cohomologies. Okay.
There any need to renormalize at this point?
To renormalize? No. I mean, I haven't talked anything about the coupling. Oh, there is a question about whether the Q cohomologies get renormalized. And it's basically a conjecture, but there are some arguments to say that the Q cohomologies at one loop stay the same. Yeah, let me not go into the details of that, but it's in
so you computed that in free theory, basically, or what do you do when you do computation?
No, they do at order lambda. You can compute the cohomologies at order lambda. And then the assumption is that this does not get further loop corrections, further or lambda square corrections and so on.
Okay.
Okay, right. So in Shi's paper back in 2013, they failed to find any cohomology that is not of the multigraviton type. But then it was last year, Chang and Lin, which is the second paper in that list, found the first example of a non-multigraviton cohomology. And this is at n equals 2, which is exactly what we're going to study today. Right, so, and then moving further, like building on this development, Seok Kim, Sunjin Choi, Lee and Park, they found an infinite family of non-multigraviton states, of non-multigraviton cohomologies. So I should probably stress at this point that a cohomology class or a cohomology representative is not necessarily the BPS state in that class. So the BPS state would be representative plus Q exact. And this Q exact is something that was, what's the form of this Q exact state was not computed in this paper. What they have is just the cohomology class and a representative. And what we wanted to do is like look into it and try to find the exact combination that gives us the BPS state. Because then you could look at correlation functions and so on. Okay, so that's the setup. Now, how do we find a BPS state? The actual state, we look at eigenstates of the dilatation operator. The anomalous dilatation operator. And this, so basically null states of this anomalous dilatation operator should correspond to BPS states. Okay. Let me go back here. Okay, so in n equals 4, we're lucky because we have a very nice formula written down by Bizert for the one loop dilatation operator, also called the Hamiltonian sometimes. And this is known for any integer, for any n, and at order lambda, that is. Okay, so this dilatation operator, of course, acts on local gauge invariant operators, which are, as I mentioned, traces of polynomials in the letters. And let me write down the form of it, which is okay, now there's a few things going on here. So firstly, the most trivial thing is this -1 to the power AB is fermionic if both B and D are fermionic, otherwise it's is -1 if B and D are fermionic, otherwise it's +1. And then we have these W's, which are the letters that are these letters. And then we have W hats, and these are derivatives with respect to the letters. So for instance, you have WA hat with gauge indices AB and WB with gauge indices CD. A and B are the adjoint indices. And it acts in this manner, delta AB times delta BD delta CA minus 1 over n delta BA delta CD. So this is just the SUN propagator, and if you want the UN, you'd get rid of this part, the trace part. Okay, and also finally these coefficients that I've written down here are computable by an explicit procedure called the harmonic action. I'm not going to go into the details of this, but it effectively amounts to shuffling around the indices here, like the ij's and the alphas, with some weights, and you count all possible ways of shuffling these letters. And that gives you this CACBD, which was also written down by Bizet back then. Right. So this is at order lambda. So D equals D0 plus lambda H. Yeah. Okay. Right. So one thing to notice straight off is that this H removes 2 letters and adds 2 other letters. So clearly it preserves the length of the operator it acts on. And of course, it preserves all the quantum numbers as it should. Right, and another feature that I will show with an explicit example is that at large n, this H, if it acts on a single trace, it produces a single trace plus 1 over n times a double trace. So if you go to n equals infinity, this term drops off, and which is exactly what we expect. Okay. So now that we have this nice formula for the dilatation operator, we can construct a mixing matrix by picking some basis. Right. So let's say you pick some basis OI and you act with H on it. And this gives you some Hij, Oj, sum over J. Right, so this Hij will be a function of n. In fact, it will be a very simple function of n. It would H planar plus 1 over n H non-planar. So because we're at one loop, the only dependence is 1 over n. So this makes it very convenient to analytically continue this for different values of n. And we'll see some nice features when we do this exercise. Okay, so there's some subtleties about it, which again I'll come to with when I discuss an example of this. And another thing I should note here is that picking a basis is an n-dependent exercise. So, number of independent operators changes with n. This is because there exist trace relations at finite n. These you can think of as consequences of the Cayley-Hamilton theorem. That is, if you take a very large trace, say trace a to the power n plus 1, you can relate this to smaller traces, like trace a to the n1, trace a to the n2, and so on, a sum over these, which we would naturally expect because at finite n you only have so many independent objects inside any single matrix, n by n matrix. Maybe I'll just give a simple example of something like this. So in SU2, if you take trace x to the 4, this is related to trace x squared, trace x squared. So the point is, you have to be careful about picking a basis. At large n, there are no trace relations. So another feature is when the length is less than n, there are no trace relations. Okay. Bigger? Okay, sure. The length is smaller than n. Then yeah, that's, okay. So yeah, let me now go into an example of that will show what's going on. I'm going to work in the so-called SU2 sector. So what this means is, out of all the letters which I erased, let me only keep 2 letters, which are, say, Z equals 512 and X equals 523. This turns out to be a closed sector. That is, there's no mixing between operators made out of these with the other fermions and derivatives and so on. Right, and because there's no mixing, the Hamiltonian simplifies significantly, and it just looks like this thing here. So trace x z x hat z hat, and also there's no need for normal ordering because the derivatives are all on the right anyway. Right. So now in this sector, let's look specifically at operators of length 6. Just to pick a small example, made out of 3 z's and 3 x's. So something like trace, I don't know, x cube, z cube, and so on. And let me further restrict to operators that are next to highest weight. So what I mean by this is, you can consider highest weight operators, that is things that are killed by J plus. Right, so these would only mix amongst themselves. But then you can consider the next level, which is things that are not killed by J plus, but killed by J plus squared. This is just because the highest weight sector is a little trivial. But once you do this, you end up with 6 operators. Okay, let me write down one of them. Yeah, and then you have so on up to V6. And now we can just go through this exercise of acting with the Hamiltonian on these states and computing the mixing matrix. But let me maybe evaluate one term to show what are the bulk of the computations we did in this project. So let's say we want to act the Hamiltonian on just this part. I can write this trace z cube x cube as something like, I think I need more space. Right, so we want to act here. I've drawn a trace, and of course these lines represent gauge index contractions. And we can now take one of the terms in the Hamiltonian over there. Let's say something like z x hat z hat. Right, and then we act this on this. So one index contraction, I should probably. Right, so now you can contract this z hat, say with that z over there. Right, so then this goes and hits here. Oops. Something like this. Of course, this z hat can also act on one of the other z's, but anyway, you do that, and then you get z x hat, and then z x, and then another z. Right, and now you can take this x hat now and act. Of course, there's other terms here. Now you can take this x hat and act on, say, this x, which gives you this contraction. And that gives you trace zx, trace, what's left? xz, xz. But you can instead also contract it on something else. Let me see what's. I think I kind of messed up what the example I had in mind was. Anyway, if you basically do different contractions, you can also end up with something like 1 over n, n times a single trace. For instance, maybe if I swap these here, you can see what would happen. Yeah, it's a bit sloppy, but if you contract things right next to each other, you get a closed loop, something like this, times this, right? So this gives you a factor of n, and that's exactly what I've written here. So all this is to show that when you split traces, you have a result which is suppressed by a factor of n compared to when you don't split traces, as I was saying before. But anyway, this is basically how you do it, and as you can see, it gets tedious quickly. So we automate this by putting this in Mathematica and hit Shift-Enter, and you get this matrix. Yeah, a 6 by 6 matrix. Let me write down maybe a few entries, which is actually quite pointless. Yeah, you have basically a 6 by 6 matrix. And now you can diagonalize this matrix. Look at the eigenvalues, and they basically satisfy this equation. Okay, so right away you can see that there are 3 zero eigenvalues, and this is some simple polynomial in gamma and n. Right, so then you plot the solutions of this, and they look as follows. You have n on the x-axis, gamma here. 3 of them are along the x-axis, so there's 3 lines here, different color. And then you have something like that, and then another which goes like that. And okay, the scale is clearly off, but this is the plot you get. Right, so there's some weird things going on here. First of all, it looks like if you have a branch cut and complex anomalous dimensions, so that seems weird for, at least at integer n. For instance, at n equals 2, we shouldn't have any complex dimensions. Well, the resolution is precisely that this basis is really only a basis at large n. So once you come to finite n, there are trace relations, and some states are killed off. And let me just point out which states die off here. One of them gets killed off here, another here, which is okay. And then one gets killed off here. And then one somewhere here. So yeah, so this state, well, actually, I should probably have mentioned, I've only plotted the real values here. This dotted line corresponds to 2 complex conjugate eigenvalues. Right. So if you look at n equals 2, this slice, here everything should be perfectly kosher, no complex or negative anomalous dimensions. Note that negative anomalous dimension is also disallowed because we are in a sector which is classically BPS. So then we would violate the unitarity bound. But in any case, yeah, once you mod out by trace relations, everything's fine. Let me see if I have anything else to say. Yeah, so another feature to notice is that we have these states with exactly 0 anomalous dimensions for any integer that is bigger than 4, right? And these are precisely the multigraviton states that I was talking about before. So for any integer here, you have 3 states that are identically 0. And then as you reduce n, they get killed off one by one, and n equals 2, they're all dead. Now, can we have seen this in some other way? Well, the answer is yes. The multigraviton operators representatives that Xi and Qiming Chang found, they corresponded to cohomology class. They were representatives of cohomology classes, as long as n is bigger than probably put this away. Yeah, so good question. The question is how much of this is supposed to be valid beyond one loop. Right, so as I was saying to Slava earlier, all we do is indeed at order lambda, but then there is a conjecture with some arguments which say that the weak coupling BPS spectrum is the same as the strong coupling BPS spectrum. But so at lambda equals 0 versus lambda small, there is, of course, a discontinuous jump. But then the assumption is that as lambda small versus lambda large is the same. Yeah, so the basis is that in perturbation theory, you can always renormalize such that the Q remains the same. The action of Q remains the same. And all the lambda dependence goes into Q dagger. And therefore, the cohomology classes do not get loop corrections beyond the first order. Okay. But yeah, this is still. There are some cases
So
like n
one
equals
thing
1
you
in
could
which
check. One thing you could check is whether the recombinations are allowed by short multiplets recombining into long all happen at one loop, because we can count from the superconformal. We can compare the superconformal index with the states that you find.
right.
And the question is whether all recombinations that are allowed actually do occur at one loop. This is something you could check.
But how do we look for recombinations that are? We'll have to look at which
No,
multiplets are allowed.
That's not hard.
Yeah, I mean you can do it in
That's
specific
just
cases.
representation
Sure.
theory. But the question is, are there operators that a priori can recombine and they do not recombine at one loop? Maybe they want to recombine at two
Right.
loops.
Yeah,
That-
you can do some checks like this, but then you can't. That's not a proof, right?
Well, but that would make you nervous, right? If there are
Yeah, sure.
operators that remain whose anomalous dimension is 0 one loop, but they are allowed to recombine, then most likely they will recombine at two loops. I don't
Yes,
think
yes.
that happens, but it's something that could be checked.
Yes, I agree. Yeah. Okay.
But turning this argument around, what is the possibility of some inverse recombinations happening at some finite value of lambda? Like just some state, which became, I don't know. But do you understand what I mean?
And the answer is no, that cannot happen, because that state at that point is alone, and it doesn't have any partners to recombine. Okay, so unless barring very exotic word crossing phenomena we don't expect here, that should not happen.
Okay. Sorry, where was I? Talking about multigraviton states. Right. So the multigraviton representatives, these exist as long as their length is, which is it now, less than n. Right. So as you reduce n, some of these multigravitons might go away, but you basically have an infinite number of zeros along the x-axis, and therefore by analyticity, because these gammas are solutions of these finite polynomial equations, they must lie exactly along the x-axis. Right, so now let me draw a distinction between these and 116 BPS black holes. So first off, at large n, the only operators that have protected anomalous protected dimensions are multigravitons. This with order 1. Okay, let me say it again. The only operators with order 1 energies that have protected dimension are multigravitons. So anything that is not a multigraviton should start off with some anomalous dimension here. Right? So the black holes should start off with some anomalous dimension at n equals infinity. And then also, let's say you have a black hole which is here at n0, some n0, a black hole state. As you change n, it cannot continue to lie along the x-axis, because if it did, then it will keep going by analyticity. So the generic situation is something like this. So that is, as you tune n, you start from a black hole state, BPS black hole state, and then it goes to some non-protected state at large n. And this is, in fact, what we find, as I will discuss in a bit. But any questions so far?
Don't want to, so this state that you call black hole state at n equal n0, do you still call it black hole state at n larger than n0, or do you call it something else?
No. At n equals infinity, this would be something, a finite energy state. So of course, it's not a black hole. It's not scaling like n squared at this point. So this is order n0 squared.
Yeah.
And because we're doing one loop, this order n0 stays the same. So at this point, it would be some gas of strings. And then as you reduce n, it becomes a black hole at some n0.
Okay.
Okay. Now let me move on to the quantum numbers of the cohomology found by Chang and Lin last year. So okay, but before that, yeah, let me talk a little bit about this 116 BPS states. So first off, as I've said it a bunch of times now already, we want things that are killed by both the Q and the S. Specifically, this should also hold at g equals 0, right? So this restricts the letters that occur in your operator. In particular, remember before I had phi ij, psi I alpha, psi bar I alpha dot, f alpha beta, f alpha dot beta dot, and then also the derivatives. If we want a state to be a 116 BPS state, then not all of these letters can occur by this condition. And in fact, this kills off, let me see, what does it kill off? It kills off the f alpha dot beta dots. And you're only allowed to have f plus plus here. And this is plus alpha dot. And yeah, I'm not going into the details of how you get these conditions, but this is simply the simple exercise of imposing this anti-commutator vanishes. So this is I goes from 1 to 3 instead of 4. Okay, so we have a restricted set of letters, and we make words out of them. But also, instead of looking at all possible operators, let's focus on the quantum numbers that Chang and Lin gave us, because we know at that quantum number there is something new going on, something that's non-multigraviton. Okay. Right. So these R1, R2, R3 are the SO6 R charges, and JL and JR is corresponds to the alpha dot index. And because JR is 0, we cannot have any derivatives. So I'm going to get rid of that as well, and also no psi bars. So at the end of the day, you only have these letters. Right. So now you try to make all possible words out of these. And turns out that there are many, many of them. So let me write down maybe one of them. Right. So you enumerate all of them, and turns out there are like 8,013 of them. But okay, you can make an 8,000 by 8,000 matrix and try to diagonalize it. But that's probably possible, but we can be a bit cleverer about it by leveraging some more symmetries. Okay. So a few facts we know about this particular black hole are that one, it is a primary under PSU 1,2/3. This is a subgroup of the full algebra of n equals 4. In fact, this is precisely the subgroup that preserves the Q and the S that we fix. If it was not a primary under this, we would have seen other black holes in this extensive search by these authors. But because this is the first one we see, it should be a primary. Similarly, it should be a singlet under unbroken SU3 R charge. Yeah, so you have SU4 R charge, and you fix a Q and an S that breaks it to SU3. And it's a singlet under this, because again, otherwise we would have seen more black holes that are rotated by this SU3 R charge, and we don't see any more. And then finally, there's also the condition that, okay, so in addition to this symmetry, you also have a charge conjugation symmetry on, that is, you take SUN and you conjugate that, right? So this is also a symmetry, and it's called parity, because it's different from the space-time parity. And the black hole turns out to have even parity under this operation. So yes, black hole. Okay. So yeah, you have these conditions, and all of them are simple linear conditions that you can impose on those 8,000 states. And once you impose them, you end up with a much simpler 69 number of operators. And now we're in much better shape because we diagonalize it. How long do I have more? Okay, around 15 minutes, I guess. Okay. Okay, so yeah, you write down a 69 by 69 matrix and you diagonalize it, and you get a plot that looks something like this. The lowest trajectory is exactly the expectation that I was talking about before. And this here is n equals 2 black hole. And then you have all these other states. There's 69 of them, start off all sorts of ways. And then you can have, right, so these are operators of length 7, right? So as soon as you go lower than 7 in n, so let's say this is 7, this is 6, and so on. At n equals 6, for instance, or you can start seeing weird effects like those branch cuts that we saw before. This is the best I can do without slides, but right. So you see stuff going on here. It's a crazy plot. You can see in our paper, but you can nicely see this black hole state at n equals 2. Right. And at this point, the black hole is given by this expression. It looks long, but keep in mind it's supposed to be a black hole, so not too bad, I'd say. Yeah. This queue is the same queue, but acting at order lambda. But in any case, I've written it in this form to condense it further. Oh, yeah, I should probably mention these brackets are just traces. Yeah. Okay. And also, this is clearly in this form. There's something that is q closed plus q exact. So this is exactly the representative in the cohomology. So this is closed, and this is q times something, so that's exact. Okay, so we've accomplished what we set out to do, but then there are a few more things we can learn. Firstly, now that you have this state at large n, you can actually look at this at large n, and one can ask what it is. Turns out to be an entangled triple trace made out of a Konishi multiplet operator and 2 BPS operators. By BPS, I mean half BPS. Or, no, just BPS. They're actually gravitons. And there is a whole bunch of entanglement between them. You can explicitly write it out in this form, and it turns out to look something like, I don't know if I have it here. Oh, I do. And then entangling operator. Right. So it's a cute thing here. So what this entangling operator does is it removes some charges from here and puts the charges in here. So for instance, one term is something like q something something tensor s, and then you have so on, so on. This q, for instance, acts on the left-hand side, and the s acts on the right-hand side. And we have such an expression. There are like 13 terms here, so you can think of it as 13 entangling bits. Right. Yeah, I mean, so at this point, you can also put some words to what we're doing. So at large n, you have a gas of strings, a super entangled mixture of strings. And then as you reduce n, you can interpret that as increasing the gravitational coupling between these strings. And as you reduce g further and further, increase g further and further, at one point, it collapses into a black hole. Yeah, so that's a nice picture. And okay, so what more can we say about this state at large n? Now that we're at large n, we can use integrability methods to continue this also to strong coupling. Right, so we can put one more axis to this plot, which is what I've done here. So this is the coupling, and at n equals, and also I flipped the axis to 1 by n. So at n equals 2, you have this black hole. At large n, you have the Konishi, and now you can use integrability to continue this to strong coupling, and you get a dimension which scales like lambda to the 2 lambda to the 1/4, which is what Tobias told us yesterday. Right. Now, so this is with integrability. Now, if you instead start at large but finite n, so instead of starting at 0 here, you start with like 1 over epsilon. Oh, sorry, 1 over something very big. I don't know, 1 over infinity minus. Right. So then you don't have integrability anymore. Integrability is broken at finite n. So then you can actually mix with different multi-graviton-like states. So let me be a little bit more precise. Right. This is delta, this is, yeah, okay. Oh, that's so much better. Okay. Uh, okay. So you can plot this delta versus lambda. For instance, if you look at, say, the Konishi, it would do something like that. So at weak coupling, it will start off with a slope of something like 12 lambda, which is the one loop anomalous dimension. And at strong coupling, it goes to 2 lambda to the 1/4.
When do you say Konishi, do you refer to that thing which involved entanglement? Or how does
Yeah,
this
yeah.
entanglement influence?
Yeah, this state, for instance.
But what was the role of the entanglement?
It's just an interesting feature we found. Like it's
Yeah, but when you compute anomalous dimension, does it play a role?
no, it does. At large n, it does not, because the dilatation will just go through if you act with it.
Okay.
Yeah, okay. So maybe I should be a bit more clear. So this this entangling operator is q times s. Like so, it's every generated times its conjugate. So it has no dimension. So
Okay.
qd goes through. Okay. Right. So you have something like this. This is any state, any string state would follow a similar curve that's not protected. And then you also have these multigraviton operators, multigraviton-like operators. So note that you could have, for instance, something like trace z squared, right? So this is a genuine multigraviton operator which will have protected anomalous dimension at any n and lambda. But then if you do trace z squared, trace z bar squared, this will start having corrections. So this will have some 1 over n corrections, and it will have a binding energy of order 1 over n squared. So I'm going to call these multigraviton-like operators. They, at large n, they have almost horizontal trajectories. But then they could, if you go to smaller n, they'll start deforming. But now let's say we're at very large but still finite n. And if this operator and these operators have the same charges, then although they don't mix at large n, at infinite n, they can mix, and then you'll have a resolution of this crossing. So something like this. This will go something like that. Go there. It will go there. Right. So this is what we generically expect to happen once you go away from perturbation theory. Right. So which is why I get this staircase-like pattern. This is not something we computed like exactly. Of course, we can't. But this is the expectation. So now the story is at strong coupling at large n, you have again a bunch of gravitons. And then as you follow it, it then collapses into graviton. So it changes its behavior depending on how big your n is. Okay, so I have one last comment.
How many steps in the staircase do you expect?
We did not do this exercise, but in principle, you can just count how many of these multigraviton-like operators we have in our charge sector. We have not done this, but if you do that, you can estimate, and also how many other non-multigraviton, non-protected operators there are. For instance, if you had something else like
why can you have more than one step? Because it looks like after one
oh
step
yeah,
you're
that's exactly what I'm saying. If you have multiple other non-protected operators, say something like this would go like this, and then this would go here, and then there.
Okay.
So this would be something nice to see, but we've not done that. Okay, right, so the last comment I have is about this black hole here. So note that this black hole, as you change lambda, staying at n equals 2, we expect it to have protected dimensions, so gamma will continue to be 0. But then if you change n, it will start having an anomalous dimension here. So here, it's a short multiplet at n equals 2. But at n equals, so at 2, this is some short multiplet. Let me just call that m1. And at n equals 2 plus epsilon, this would be some m1 plus m2. So this multiplet recombines with something when you move away from 2. But then this recombination does not happen as you change lambda, which is weird because if you have a multiplet with the right charges to recombine, we expect it to happen. Yeah, I mean, it would be some sort of a conspiracy theory that it does not recombine here. And the resolution is that this multiplet vanishes by n equals 2 trace relations. So then here you have nothing to recombine with, but then as soon as you go away from n equals 2, you can make a long multiplet. Yeah, I think that's all I have to say. Thank you.
Questions? We are well on time. Yeah.
I didn't quite understand. So if you have a state at n equal 2, how do you continue it in n?
Because you have the dilatation operator that acts at any n. So you diagonalize it and see which is the trajectory that is connected to this.
I see. So, so for example, for that one over there, that's written only for n equal 2, right?
Exactly, yeah.
And then at higher n, does it look similar or does it?
No, it gets significantly more complicated. It starts having like, it is an 8,000 term expression.
I see. And I had another question. Do you know if anything's known about a similar problem in ABJM theory?
I have no idea about that, no.
Any other questions? Let me, yeah, so then let's first thank Arish. And let me just